Hello everybody, Mr Fizz here. First of all, I've got to apologise for my appearance. It's because the old geezer who made me in a bit of a rush and he wasn't very clever. Anyway, today we're going to do some more Fizz. We're going to talk about light and heat. Yes, light. Oh my goodness, that's better. And heat. That's lovely and warm, right? That radiant papers. Oh no, I've forgotten something. I'm made of plasticine. Oh dear. Oh, bye.
Hello everybody, we're going to talk about light. Do you know what? You can't see light. Here's proof. That's a laser. I turn it on, press the button, and you cannot see the light. I can prove it's there. Watch. Actually, it's alright, it's only light. Red laser beam. So you can't see the beam. What that means is that when you see things like this, the Starship Enterprise sending out its lasers, you wouldn't see them. You only see light if it reflects off things, and there's nothing there, it's space. Actually, having said that, you wouldn't even see this because it's not near the sun, and so it's not getting any light falling on it. So when you see like that, wouldn't really happen. Also, by the way, there's no sound in space because sound, if you've been paying attention to my first video, sound needs particles to travel. And there are no particles in space. So when you see these spaceships going on, pow, 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 with their laser torpedoes, pow, pow, what it would really be would be although in fact you wouldn't see it anyway because there's not enough light there. Okay, now let's have a look and see that we can see where the laser beam goes if it reflects off particles. I'm going to use some smoke. So you can see it on the wall, you know it's there, okay. What I'm now going to do, and we can't see the beam, you cannot see light, but blow the candle out and you can see the beam now because it's reflecting off the smoke particles. Look at that. The main question is, what actually is light? I don't hear your reply, so I'll tell you. It travels in waves, and it's what we call an electromagnetic wave. That means there's varying electric fields and magnetic fields. Sounds a bit weird, but nevertheless, when it interacts on the sensors in our eye, more about those later, then it will actually send messages to the brain. So electromagnetic waves, and actually you've heard of a lot of different sorts of electromagnetic waves. They're all the same thing, but different wavelength, from long ones down to very, very, very short ones. This is what they're all about. So this is the list of electromagnetic waves, starting with the longest ones up this end. And you've heard of them all, because the longest ones are called radio waves. That does, of course, include tele, because that comes over a radio wave. It's an electromagnetic wave. Then you've all heard of microwaves. Now, microwaves don't only heat your food up, but they're used in radar and they're used for telephones as well. Next comes something called infrared, and that basically is the same as heat radiation. And you've all seen pictures of police camera action where they've got a special camera that does thermal imaging. Well, thermal imaging is looking at infrared, and anything that's warm or hot gives out infrared radiation. This is light, that's what we're talking about here, light. And then we've got ultraviolet. Not ultraviolet, as some of my pupils used to write. And ultraviolet, it's got more energy than light, so as we get progressively to the right, each bit of the radiation has more energy. Ultraviolet's got enough energy to make things fluoresce. And of course you all know that when you go to discos, as you U3A lot do, you get this sort of fluorescence on various materials, and that's caused by ultraviolet lights. Now, shorter than that, you've also heard of something called X-rays. These have got even more energy than ultraviolet, so much energy they can get through your skin pretty well. Not quite so well through your bones, so they cast a shadow on the detector. And finally, the shortest ones are gamma rays. We can produce gamma rays, and it's only happened in a relatively recently, but they are some of the sorts of radiation that comes from radioactive materials. Now, quickly back to light. You can see that this is infrared, and you can see this is ultraviolet, but light consists of loads and loads of, well, an infinite number of wavelengths from this end to this end, and they all give in our brain different colours, and probably you know them because they're the colours of the rainbow: red, orange, yellow, green, blue, indigo, violet. And you might have remembered from school, Richard of York gains battles in vain. The reason indigo is there, because it's not one we normally consider. Newton put that in because he wanted there to be 7 colours, because it represented the 7 keys on a piano, A, B, C, D, E, F, G. So it made a complete octave to him. Now, all these electromagnetic waves travel at the same speed. We call it the speed of light because that's most familiar to us, and it is 186,000 miles per second. That's 300,000 kilometres per second, or the equivalent of 7.5 times round the equator per second. So it's, as far as we're concerned, it's instant locally, but not on a longer distance. For example, the light takes 8 minutes to get to us from the sun. If the sun went out now, you wouldn't know for 8 minutes. And our nearest next star after the sun, it actually takes 4 years for the light to get to us. So that's a long distance. There was a great story when the Americans first went to the moon, and they landed their buggy on the moon, and they set a camera to watch it going up, and they had a remote control back at Houston. Okay, so they're ready to blast off, and it's 5, 4, 3, 2, 1, blast off. And as it blasted off, they pulled back on the joystick for the camera to make it go up, but they've forgotten that it took 1.2 seconds for the radio waves to get to the moon, and so all you saw was the buggy going whoosh. And then, as the camera panned up 1.2 seconds later, there was empty black sky. Now this is a cross-section of the eye, and this is a happy section. But we've been there before, so let's go back to the eye. Now, as I used to tell my pupils, the eye lends itself to all sorts of humour. And I know I've got a nerve telling you this, but I better stop because they only get corny. Well, that was 5 yolks, and here's another 6. There, look, how to make a perfect pentagon using 6 eggs. Pam discovered that when she was baking once. Anyway, I expect that you want me to change the subject, so I shall. Of course, an earth is an earth. A little international pun there. That's what the eye would look like in cross-section, and they're the main bits of the eye. Now, in the retina, the bit at the back, there's 2 lots of receivers. They're called rods and cones. And the rods are to do with bright and dark, so they're very, very sensitive. They work even when there's not much light. But the cones are to do with colour. Easy to remember. Cones for colour and rods for not colour. So, rods and cones. Now the cones let us determine what colour we are seeing, but there is no such thing as colour. I bet you didn't know that. So here's a question for you. See if you can get it right. What colour is a red book? Think about it. Actually, it's got no colour. Now, here is a question for you. What are the three primary colours? And my guess is that most of you will answer this: red, blue and yellow. Well, that's wrong. They're actually the three primary colours of paint, but paint acts by absorbing some colours and only reflecting some others. See what's coming on soon. The three primary colours are red, blue and green. And that's because in the eye we have three lots of cones, ones which respond to what we call red wavelengths, one which we call blue wavelengths and one green wavelengths. Here's a little diagram showing you the response to the three different colours, as we call them, and you can see that they can get a mixture there. Any colour can be made up for our brain for combinations of red, blue and green light of different brightnesses and different mixtures. And this little diagram here shows exactly that happens. They've got the three primary colours and the three secondary colours. And if you don't believe me, then just pause the picture for a while, get a magnifying glass and look very closely at your screen, and you'll see that where it's shaded red, only the little red pixels are lit up. Where it's magenta, the red and the blue pixels are lit up. Where it's white, the red, the blue and the green are lit up. And those combinations make our brain see those colours. Now let's have a look at that question. What colour is a red book? Here's the red book, and this is you looking at the red book. Well, it might be you a few years ago, or I suppose we should say it might be you before your gender change, or maybe even after your gender change. But anyway, this is you looking at the red book. And white light from the sun or from all around comes onto the red book and hits it. Now remember, white light's made up of all the colours of the rainbow. The thing is that the pigment in the red book actually absorbs lots of colours, and it absorbs all the colours of the rainbow except for red, which it reflects. So therefore our brain receives waves which tell us the signal to the brain red. In a similar way, supposing it was a yellow book, then the pigment absorbs everything except red and green. And interestingly enough, when red and green both go into our eyes, our brain interprets it as what we call yellow. So there we are. There's not really any such thing as colour, just pigments which absorb different colours. Now let's have a look at how light behaves, because that's the most important thing for us. And we'll start with mirrors, which on reflection is a good idea. Now, we do see ourselves in the mirror. Actually, we don't. We see an image of ourselves. And in fact, I can't see an image of myself in the mirror at the moment. I'm doing a trick that they do in telly. On telly, you see someone sitting at a mirror and you can see them looking at themselves, but they're not. I'm actually looking at the camera. It has to be that way because the camera is looking at me, because the light reflects off at the same angle as it goes in. So it's going boink, boink, like that. Now when you look in a mirror, you're not seeing yourself, you're seeing an image of yourself. It's a bit like looking through a window at seeing another you back to front over there. And actually, if you think about it, the you over there seems to be the same distance behind the mirror as you are in front of it. And that's right about reflections. Two things. One, the image is the same distance behind the mirror as the object is in front of it. And secondly, it's back to front. The proper name for that is laterally inverted. I'm sure you want to know why that is. I'll show you. Now this is a mirror. Here is the top view of a man looking in a mirror. Oh, actually, we shouldn't really be sexist about that. It could be a lady with a bald head, or maybe a transsexual person who doesn't like hair. Anyway, what happens is when you look into a mirror, you don't see yourself, you see an image of yourself. And it's a bit like looking through a window and seeing another one of you over there, but back to front. We'll explain that later. Now, how does it work? The point is that everywhere you see the image, the point of the image is the same distance behind the mirror as the object is in front. So this head, the image of the head would be about there, with his nose, two ears, and so on. So there's the image. And the image is the same distance behind the mirror as the object is in front. And that's why, if you think about it, looking in a mirror is a bit like looking through a window at another one of you the same distance away. That's why they have mirrors on the wall of many restaurants, to make the whole place look twice as big. This, as you can see, is the letter L, and here is our mirror. Now, you'll remember from the last bit we just did, well, if you don't, you passed it now because you should have remembered it, that every point, the image is the same distance behind the mirror as the object is in front. So the image of that bit is about there. The image of that bit is about there. The image of that bit is about there. So what do we get? A back to front L, lateral inversion. You might think, well, what the L was that about? Well, it's very useful if you happen to see an ecnalibma. An ecnalibma, I hear you say, with one accord? Yes, here's an ecnalibma. So if you're driving along and you look in your mirror and you see a great big white and yellow thing with blue flashing lights and sirens going, you now know what it is. It's an ecnalibma. Well, having just talked about reflection, I went and had a cup of tea, but you didn't know that. That's magic, isn't it? But now we're going to talk about something called refraction. Now, when light goes from a less dense to a more dense medium, that's what they say in the books. And I always used to think, when I heard more dense medium, I thought of a very thick spiritualist. But anyway, I say when it goes from a less dense to a more dense material, or the other way around, it changes directions. It gets bent. The ray of light gets bent. So the proper word is refracted. Okay, so it will refract into the water or into the glass and change direction. I'll show you that in a minute. Well, now actually. Now, if this was air and this is water, we find that light actually goes slower in water. The more dense material, the slower the light goes. And so what that means is it's not going as quickly here. In fact, in water, it goes about 2/3 the speed of in air. Now, let's imagine this is a beam of light falling on the water, and these are the waves. Because they slow down once they're in the water, they end up closer together. So we say in physics the wavelength has changed. That doesn't matter too much, but the point is it's going slowly. And if it's hitting the surface absolutely flat on, it carries on in a straight line. However, let's look at the situation if this beam of light is coming at an angle to the water. Right. This end slows down, while the other end, this end, is still going fast. So basically, in the time it's taken for the light to get from there to there, it's only gone about this far over here. And so what happens is that wave gets bent over, and the new ray goes through the water like this, and hey ho, the direction has changed. If you like, it's bent. We say that at GCSE to a little bit, but basically the proper word is it is refracted. That is refraction. This picture's a bit better than mine, and it comes from a book, so at least you know I wasn't telling fibs when I drew it. The bent stick effect is quite a well-known phenomenon, and it's caused by refraction. You can see the picture here. And also, refraction causes the water to look less deep than it really is. It's shown here looking at a fish, and the fish appears shallower than it really is. So if you happen to be a spearman living in wherever they live, then you know to aim lower than where the fish seems to be. Have you ever wondered, you might not have done, why, if your shirt gets wet, it goes dark? It does, doesn't it? Or if you've been for a swim and your hair's wet, it looks black, which is actually better than the normal colour, isn't it? Why does it look dark? Well, we see anything because light reflects off it. But when light falls on this bit, there's water, and some of the light will refract into the water instead of being reflected back again. And so therefore it looks darker there than it does elsewhere. Good explanation, and now I've got a wet shirt. Magically dry again. How about that? Now, here's a clue to the next bit. You can carry on the rest yourself if you like. Ever wondered why stars twinkle? I'll explain using a diagram. Now, as you can see, this represents the Earth with the atmosphere, and that's you over on the right-hand side. Please note this is not drawn to scale. Now, if a ray of light comes from a distant star to your eyes, it goes through the atmosphere. But the atmosphere's got lots of different temperatures at different places, and therefore different densities, and therefore the light refracts backwards and forwards. So when you look at the light from this star, it's wiggling backwards and forwards, so it looks as though it's twinkling. In other words, the brightness is changing. If you're on the moon, where there's no atmosphere, then they don't twinkle at all. They're all fixed brightness. Now, here's something else that's interesting. Supposing this wasn't just any old star, but supposing this was light from the sun, and the sun, as you all know, is our nearest star. Well, when light from the sun comes in, it's not going to vary and twinkle because the sun's so big in the sky compared to point stars. But what does happen is a thing called scattering. Now, scattering means that some of the wavelengths are pushed off in different directions. And the shortest waves, that's the bluest of colours in our spectrum, are scattered most. So what happens is, over this length of atmosphere, due to all the little particles that are there, the light gets scattered, but mainly it's the blue light that gets scattered. So if you happen to be standing here and look upwards, you will see blue light. Aha, the sky is blue. Or if you're out in space and you look towards the planet, it looks blue. How does that leave this person? Well, he's got all the colours of the rainbow. You take away the blue end, and what are you left with? The red end. Sunset. Ta-da! Now, we know that all the colours of the rainbow come from the sun, that we call white light. And you probably know that if we shine white light into a prism, the colours split up. Now that's because different colours, which are different wavelengths or frequencies, different colours refract by different amounts. The red doesn't refract too much, the violet or blue end of the spectrum refracts more, and we usually remember that by blue bends best. So have a look at this diagram and you'll see why we get a spectrum out of a prism and how we don't get a spectrum out of a prism. The white light comes in from the left and starts to refract. All the colours refract, but the blue bends best. So we've got separation already. And by the time it gets to the other side of the prism, it separates even more because of the angle there. Now, this is not how it works. Look at that. These are the sort of pictures you get on the internet sometimes, so don't believe everything you see. How can it possibly bend upwards when it hits the first surface? That's awful. It bends upwards at the second surface. This one completely both wrong. That one, goodness knows what's happening there. And this one starts to magically separate but have no refraction at the second surface. So don't believe all the pictures you see. Well, what we're going to have a look at now is how light escapes from water and it bends the other way if it's going out of water. But what happens if we increase the angle of the light on the surface? We get a strange effect called total internal reflection. Now, to show reflection and total internal refraction, I've got a bowl here of water with just a little tiny bit of milk in it. Don't tell Pam that I'm using this bowl because it's her favourite. I'll get told off. Okay, I'm going to shine the laser, which is a green laser, straight upwards more or less. And you should see the beam going up. And with a bit of luck, with my fingers, you'll see where it comes out. There it is. Okay. So what I'm going to do is slowly make the angle bigger, and you can see it's still on my hand. It's still on my hand, but we're getting down quite an angle now, and still on my hand, still on my hand. We're nearly level with the surface, and all of a sudden it doesn't go out anymore. It cannot escape. It is totally internally reflected, and the top behaves just like a mirror. Good, eh? If we have a prism, a triangle of glass, where the angles are 90 degrees, 45 degrees and 45 degrees, then a ray of light which enters doesn't change direction because it hits that one at no angle, but it hits that angle at 45. 45 is greater than the critical angle, so therefore it would totally internally reflect. If it does that, it will come off at another 45 degrees, so it comes off altogether at 90 degrees to the original. Repeat the same down here, and you have the makings of a periscope. So light coming from outside goes to the periscope. The reason that's used in submarines and so on is because the reflection is perfect at the single side, much better than with mirrors. Now, supposing you use that same 45, 90, 45 prism like this and shone a ray of light into it in that way, it would do that. It meets it at 45 degrees, total internal reflection, total internal reflection. So basically, within some angles, most of the light that goes in is reflected back. Make that of yellow or red plastic, and that is a reflector on the back of your bike or your car. And if you cut it really cleverly and use something incredibly dense compared to glass, that's diamond, then just about every ray that comes in reflects back out, and so diamonds look not only very sparkly, but also the refraction causes the colours to split up from the white light. If, ladies, your diamond starts to fade and doesn't show so bright as it was before, it's not because he doesn't love you. It's because instead of being a diamond air surface, it's got a bit greasy from your hands on the back. So it's a diamond grease surface, and some light will escape out the back, so it won't look so shiny. Again, if I put my watch, there it is, into a bowl of water. So let's just take it off. Sorry about the wiggles whilst I do it. I can't hold the camera and do it one-handed. I'll just put it down for a moment. Right, so I'm going to put the watch underwater. Oh no, it's the wrong watch. Oh, not really. Okay, now I want you to watch as I slowly rotate it. We can see the face of the watch nicely, and as we get to a certain angle, it will actually turn into a mirror. Ta-da! Total internal reflection occurring at the inner face of the glass with the air. Total internal reflection occurs with optical fibres, and you're all familiar with this sort of optical fibre light, where all the light comes up from the bulb at the bottom, goes up through all the individual fibres and comes out the end. And of course you can make it nice pretty colours. Well, that's for fun, but more practical use is using it for cable connections instead of copper wires for TV, video and internet. And this is a typical section of cable. You can see all the optical fibres, each one much thinner than a human hair, and each one capable of taking 2, 3, 4,000 phone calls at any one time. So there's a massive capacity of data can go down there. If you can read the title okay, it says, do you need specs? And this is all about defects of the eye. Now, short sight is going to be dealt with first. With a normal eye, this represents the eye. Rays from a long way away come along and get refracted, bent, onto the retina to form an image. But if you're short-sighted, what happens is it bends the rays too much. And so what happens is that the rays coming in focus at a point not on the retina, so everything's blurred. And what you've got to do is push these rays out a bit. So if these rays are coming along and they can be pushed out a bit like that, then they will focus on the retina. And to do that, we need a diverging lens which has a negative focal length. So on your prescription, if it says minus, you know that's for short-sightedness. Long sight is a bit different. It means you can't see something close up properly. So what happens is rays come from that to the eye and they come to focus, but it would be back there somewhere. So it's blurred. So if you try and look at something close up, it's blurred. What we need then is to actually bend those in a bit. So these rays here, which are going out, need to come in a bit so that they end up focused on the end. We don't need that picture. It's impossible to cover everything about light, but you've seen quite a bit, haven't you? How eyes work, how specs work, why the sky is blue, why shirts get wet, well, when you throw water over them, of course they do, why they go dark when you throw water over them, etc, etc. Hope you enjoyed it. Bye bye. Oh, it's me again. I forgot to say this was meant to be about light and heat, but I thought you probably had enough for one session, so I shall do another one on heat. You have been warned. That's a threat.
And it's bye-bye from me. Bye!